Now let's think about this series. I need to compare it to something, and I'm going to try the same trick that we tried with the direct comparison test. I'm going to say when n gets really big, the larger power term, 4 times n, will matter more than the lower power term, 3 times the square root of n. So as a comparison series, I'm going to consider the series that has terms 3 divided by 4 times n. When I add these sequence terms all up in a series, I can factor out the 3/4, and I see this is the harmonic series, so it diverges. Now I found a series to compare it to, but I have to prove that that comparison is actually valid. I have to prove that these two series actually behave the same way. If I wanted to use the direct comparison test, it would need to be the case that my mystery series had bigger terms than my comparison series. But this is not the case. My mystery series has smaller terms. That means the direct comparison test isn't going to help us here. So let's try the limit comparison test. I need to evaluate the limit of the ratio of paired up terms. My ANs look like 3/4n's. My BNs, I'm going to flip them and multiply. So my top becomes 4n plus 3 root n, and my bottom becomes 3. Now I just need to figure out this limit. Cancel, cancel. This is the limit, as n goes to infinity, of 4n plus 3 root n divided by 4n. That's 1 plus 3/4 root n, because n is the square root of n times the square root of n. As n goes to infinity, this term on the right goes to 0, so this limit is 1. Crucially, 1 is positive and finite. So this is the limit comparison test telling us that these two series are indeed comparable. What one does, the other one indeed does as well. So by the limit comparison test, my mystery series does what my known series does, and it diverges. Now that you've seen a few examples, pause the video, see if you can solve this one on your own. The first thing to remember is that where we start doesn't matter. It just matters that we have infinitely many terms. I can compare this to the harmonic series. The terms of my unknown series are bigger than the terms of the harmonic series. All these terms are positive. This inequality goes in the right direction to immediately jump to the direct comparison test. No limits of ratios needed. Pause the video again. Work on this problem. The first thing that we need to do is get this into sigma notation. My numerators go 1, 2, 3, 4, 5. So my numerators are just k. My denominators are all squared, and the base is 1 bigger than the numerator. Now we need to find something to compare it to. My standard trick is I'm going to avoid the lower degree parts of a polynomial. I bet that when k is quite large, k and k plus 1 behave kind of similarly. So the comparison series I'm going to use is the harmonic series. This is a divergent series. So let's see whether our inequality goes in the correct direction to use the direct comparison test. The denominator on the left is bigger so the fraction overall is smaller. This is not the correct direction for the direct comparison test, so we need limit comparison test. So what I have is two series that I would like to compare, but I haven't yet proven that the comparison is actually valid. In order to do this, I'll take the ratio of their terms. It doesn't really matter which term I put on top. Here are the terms of one series. Here are the terms of the other. I flip the denominator and multiply. What I have now is the limit of a rational function, a polynomial over a polynomial. The top and the bottom have the same degree. That means the limit is the ratio of their leading coefficients. So as k gets really big, these terms up here and these terms up here basically look the same. Their ratio looks like 1. Our limit was finite and positive, so the comparison is valid. What one series does, the other series does as well. So by the limit comparison test, our series diverges, just like the harmonic series diverges.